So in today's video I have brought you a very nice integral. It's set as from 0 to plus infinity of logarithm x over 1 minus x squared dx. Okay, so in fact I don't think this integral is hard, because you can solve it in such simple ways. So you can also, if you want to use the complex analysis, you can do it by Residu's theorem. So we are not going to do that. So we are simply going to apply the regular theorem here. So it becomes hard if you have a plus sign here, 1 plus x squared, then we need to use the complex analysis. Okay, so anyway, you can give the hands to this problem pre-read to solution. Go ahead, pause this video when you want to come back to see the full solution. By the way, don't forget to hit the subscribe button and support our channel. So now let's jump into this integral to see what's given us. Okay, as we solve this integral, we are going to divide this integral into two parts. Okay, so this I integral is going to be the same as from 0 to plus infinity. Okay, so let's name this one as a f of x dx, which equals from 0 to 1 of f of x plus from 1 to plus infinity of f of x dx. I don't need to write the whole expression, so simply I'm going to call it as a f of x. So now let's evaluate this integral. Let's name it as a I1 integral. Okay, this one I2 integral. I'm going to transfer this, the bound of the second integral, on the same form as I have here. Okay, so I get I1 integral from 1 to plus infinity of logarithm of x over 1 minus x squared dx. By going through the substitution, I'm going to set x equals 1 over t. If I'm going to differentiate this one, I will have dx equals minus dt over t squared. So I'm simply going to exchange that. I will have a new integral. The bound from, by replacing x with 1, I get t equal 1 as well. Replacing x with plus infinity, must have t equals 0. Okay, so for the logarithm, I get log of 1 over t all over 1 minus 1 over t quantity square. This dx becomes minus dt over t square. Now we'll have a lot of cancellation here, so I'm going to flip this bound, then this minus sign will be cancelled out. Also, I'm going to take the log of 1 over t becomes minus log of t. This one I'm going to multiply, this one will be cancelled out with this t square here. Then multiplying numerator by t square, I get t square minus number 1. So at the end, you will have the integral from 0 to 1 of logarithm t all over 1 minus t square dt. So if I'm going to change the variable of this integral, it's not going to change the value of this integral. From 0 to 1 of logarithm x all over 1 minus x squared dx. If you take a look at the expression of this integral, it looks like the same as I have previously, okay, which is this one integral. So the function is the same, log x over 1 minus x squared. We need the bound. The bound equals to this one. So which means this integral equals this one. It was I1 integral, which equals I2 integral, because we need just to replace this one here into this one, is giving us the same bound. Okay, so now the original integral, which is I, is a run from 0 to plus infinity, equals 2 times from 0 to 1 of logarithm x all over 1 minus x squared dx. Now we found a nicer relationship between the first integral and the second integral. I have ended with this nice expression. Now let's get this expression at the top and continue solving it. So now we are ready to solve this integral. Since we get x is a run from 0 to 1, so we get the absolute value of x. So we get the absolute value of x is strictly inferior to number 1. We are not going to include number 1, because if I'm going to include number 1, I will have a problem in denominator. Okay, so which means x must be strictly inferior to number 1. Of course, it's positive. Okay, if you take a look at the denominator of this function, is a geometry series, which means 1 over 1 minus x squared equals the geometry series. We get a sum of x to the 2n as n run from 0 to plus infinity. Okay, I'm simply going to insert the value of 1 over 1 minus x squared into this integral. So I will have a new integral of I equals from 2, I will have 2 is multiplied with from 0 to 1 of the sum of x to the 2n as n goes from 0 to plus infinity of logarithm x dx. Okay, so since we have the convergence series, I'm allowed to take this sum outside of this integral. So I will have the following. I will have I equals twice the sum as n goes from 0 to plus infinity of the integral from 0 to 1 of x to the 2n log of x dx. Now I'm going to solve this integral. Let's name this integral as a j integral. Okay, since I have a product of two functions here, so I'm going to use integral by parts. Okay, let's set u equals log of x and dv equals x to the 2n, like this. So you know by part always u v minus v du. Okay, I'm simply going to use integral by part. So as I have mentioned above there, so you get here g integral. So looking for the primitive of v function, I get 1 over 2n plus number 1 is multiplied by x to the 2n plus number 1 is multiplied by a log of x minus another integral which is it's set as from 0 to 1. So looking for the primitive of the dv, I get 1 over 2n plus number 1 of x to the 2n plus number 1. So by taking the derivative function of log of x, I get 1 over x dx. So this one it was evaluated from 0 to 1. Simply this x will be cancelled out with this exponent, becomes 1 here, becomes x to the 2n. It's more simple to evaluate this integral as I'm taking 1 over 2n plus number 1 out of this integral because it's a constant. What I'm going to end with, I will get 1 over 2n plus number 1 is multiplied by 1 over 2n plus number 1 of x to the 2n plus number 1 is evaluated from 0 to 1. Okay, which is going to be 1 over 2n plus number 1 quinary square, because this one will be number 1, 0 will be 0. Okay, so don't forget a minus sign. So this one it will be minus sign here, but this one be careful here. So for the upper bound, it's more simple by plugging number 1 into a logarithm here. I get everything 0. But the problem with 0, you cannot plug 0 into this one and multiplying 0 with log of 0. You cannot do that. We are going to apply the limit on this one. Okay, so the limit of this one, so I get 1 over 2n plus number 1 is multiplied by x is multiplied by log of x is multiplied by x to the 2n. I'm taking 1 of the x out of this one to evaluate just this one. Okay, but remember we are going to apply the limit as x goes towards 0 from above. Okay, with a minus sign here. Okay, because we put number 1 minus this one, it is arithmetically is going to be 0 by applying the Hopital rule. But we are going to prove it. This one it's more simple to prove it. So we have minus the limit of x log of x as x goes to 0 from above. So I'm going to let's set x equals 1 over t. Okay, so I get here the following, get minus log of 1 over t all over t. Okay, then taking this inverse of this one by taking this inverse of log, I get plus sign here. This one becomes log of t. Okay, So x is going towards 0, but t is going towards plus infinity. If I'm going to apply is going towards infinity here, I get plus infinity over plus infinity, which is impossible. So when you have this problem like this, it's indefinite form. Now we are going to apply the L'Hopital rule here, okay? So for the L'Hopital rule, we are going to derivate this function. This one becomes 1 over t. The bottom one becomes number 1. So now, so as t is approaching to infinity, this one is going to 0. So which means 0 over 1, which is 0, okay? What we have ended with? I have ended with this one. So the g integral equals minus 1 over 2n plus number 1 quantity square, okay? So we have ended with this one. Now we are going to evaluate the sum of this one. Now let's get rid of this one and move on to the next step. We did the necessary steps and we end up with this expression. So now we need just to evaluate this one, okay? Let's evaluate this one as n goes from 0 to plus infinity as a converse series 1 over 2n plus number 1 quantity square. So the sum of 1 over n square equals the sum of the odd term plus even term. But here we have the odd term, which means I get the sum as m evaluate from 1 to plus infinity, I run from 1 to infinity of 1 over m square minus the sum of m goes from 1 to plus infinity of 1 over 2m quantity square. By bringing this even part to the right, I get odd plus even equals this one, okay? Let's evaluate this one. By taking these two out of these things, I have 2 square, which is 4. Let's put it outside of this one, which means 1 over 4. So, which equals 3 over 4 by this one minus this one, 3 over 4 of the sum as 1 over m, a sum of 1, m it goes from 1 to plus infinity of 1 over m square, okay? This is its more known sum. You can use the Fourier series, or you can use the Taylor expansion combining with the Euler product, okay? Then you will find this one easily. Or you can use the Riemann zeta, okay? Riemann zeta is a more powerful tool you can use because you are going to deal with any exponent of 1 over m to the s, okay, whatever. So this one equals 3 over 4 is evaluated at the Riemann zeta, at the of the Riemann zeta, it's evaluated at number 2 here, okay? So it's more simple, it's going to give us 3 over 4 is multiplied by p square over 6, okay? So which means our sum, the integral equals minus 2 is multiplied by 3 over 4 is multiplied by p square over 6 is going to give us minus pi square over 4, okay? If you want to take a look how to prove this one, so I'm going to add the proof of this one in the comment section below because I have done this one before in my old videos. So I have used here the Taylor expansion combining with the Euler formula, and also I have another video. I have also other videos using the Fourier series. I'm going to add them in the comment section below, okay? If you are interested to watch that. So now, by the way, don't forget to hit the subscribe button and support the channel. And thank you for watching. We'll see you next video. Bye.